Hi class. So the second way in which a water droplet, or in this case an ice crystal, can grow to the point where it can reach the surface without vaporizing below the cloud is called the Bergeron process. And the Bergeron process is probably the most abstract concept we're going to cover in this class. Okay, and so for the Bergeron process to take place, we have to have a cloud that is below minus 9 degrees C. And so the Bergeron process only takes place in cold clouds, which means that it's most important in the mid-latitudes and high latitudes of the world. So in our example here, we've got a cloud. The temperature of the cloud is minus 15 degrees C. It is made up of a combination of supercooled water droplets and ice crystals. And we know that the relative humidity within a cloud is 100%. Now the key to the Bergeron process is that Bergeron realized that the saturation mixing ratio around supercooled water droplets and the saturation mixing ratio around ice crystals is actually different. The saturation mixing ratio around ice crystals is actually lower than the saturation mixing ratio around a supercooled water droplet. In this particular example, where the temperature of the cloud is minus 15 degrees C, the saturation mixing ratio around an ice crystal at minus 15 degrees C is 1.03 grams per kilogram, while the saturation mixing ratio around a supercooled water droplet, that is at a temperature of minus 15 degrees C, is 1.20 grams per kilogram. So we know that the relative humidity in a cloud is 100%, so we can calculate the mixing ratio inside that cloud. The mixing ratio is the relative humidity, 100%, times the saturation mixing ratio of 1.2 grams per kilogram. So the mixing ratio is going to be 1.2 grams per kilogram. So it follows then that the relative humidity with respect to or around the supercooled water droplet will be 1.2 grams per kilogram mixing ratio divided by 1.20 grams per kilogram for the saturation mixing ratio. So the relative humidity is 100%. The relative humidity with respect to the ice crystal will be the mixing ratio, 1.20 grams per kilogram, divided by the saturation mixing ratio of the air around the ice crystal, which is 1.03 grams per kilogram. And that actually gives us a relative humidity of 117%. Now that's a theoretical relative humidity, but the importance of it is that it creates supersaturated conditions around the ice crystal and only saturated conditions around the supercooled water droplet. So over time, what's going to happen is we've created a steeper saturation gradient around the ice crystal. So the ice crystal is actually going to grow, and the supercooled water droplet is going to start to shrink. Okay, so throughout time, and as the ice crystal falls through the cloud, the ice crystal is going to grow, and the supercooled water droplets are going to shrink. And so eventually, this ice crystal will fall out the base of the cloud, and that's how we get a snowflake. Now, as I mentioned in the notes, don't think that this happens only in the winter time. Sure, this is how snow is formed through the Bergeron process, but in the summertime, in cumulonimbus clouds, which might be 50 to 55,000 feet tall, the Bergeron process is taking place in the cold part of a cumulonimbus cloud. Okay, and so oftentimes the top of a cumulonimbus cloud, you'll have ice crystals, snowflakes, and as those snowflakes fall through the cloud, it encounters an above freezing portion of the cloud, or when it falls out the cloud base, the snowflake is going to melt into a raindrop. And so if you ever went and stomped around in the puddles along the curbs of streets, the water after a thunderstorm is actually pretty cold, and there's good reason for puddles being cold in the middle of summer, and that's because those raindrops that created the puddle actually started off as a snowflake. So there you got it. This finishes off this section of Chapter 7. The last section we're going to take a look at is a section on the various kinds of precipitation.